Okay, so welcome to the PhD final defense of Zachary Lesko. Just before we get started, I'd just like to go through the procedure of what's going to happen. The first part will be a public portion where members of the public are invited. After that, I will ask the public personnel to leave, and then there'll be a committee portion with the candidate. And then the third part will be where the candidate leaves, and then the committee will deliberate. All right, so we'll just take it off from there with Zach.
Hello, my name is Zachary Lesko, and I'm going to talk about the effect of hadronization on the phi-star of the Z with the CMS experiment. So, starting out, we're going to mention the standard model. Now, the standard model is a very interconnected model that we use to describe the universe. Now, it can be compared to a fine watch, where all the parts are connected to all the other parts. So if you understand one part of it, you can get some idea of what another part is doing. Now, one of the big questions is our watch the actual correct one? Is it the real part? So when talking about the standard model, let's start talking about the fact that in particle physics we describe it as being made up of particles. Now, not only do we have talk about the particles making it up, but even the interactions of these particles we can describe with particles. Now, what is nice about the standard model is there's remarkably few free parameters. We can use these very few small free parameters to describe all sorts of ways that particles can interact. This can mean the uranium nuclei long lifetime of over 4 billion years, as well as the dynamics of a supernova. Now, the particles of the standard model that we usually interact with in everyday life fall into the electron, which most people are familiar with, as well as the up and the down quark. The up and the down quark are what makes up protons and neutrons. Now, the behavior of these particles is dependent on characteristics of the ephemeral and much heavier particles like the W. Now, let's focus a little bit on the bosons. The bosons are the force carriers of the standard model. Now, of the force carriers, the photon is probably the most well-known. It's the force carrier of the electromagnetic force. There's also the gluon, which is the force carrier of the strong force, and the Z, which is the neutral force carrier of the weak force. Now, all of these force carriers are capable of producing particles from energy. They can go from energy to mass. However, when they do this, they're only produce particles in pairs. You can produce a top, but you have to produce an antitop. You can produce a down, but you have to produce an antidown. The reason why I bring this up is the W is unique in its ability to create particles that aren't balanced. It can create a top, but doesn't necessarily have to. It doesn't create an antitop. It actually tends to create a bottom. This is important in what it can allow to happen. For example, one of the big interactions that is, well, one of the critical steps for fusion involves the W. If you want to go from hydrogen to helium, you need to make neutrons, and the weak force allows that, where in this we start with a proton and it emits a W, which then becomes a positron neutrino, leaving us a neutron. Now, the W is very massive, at over 80 times the mass of the proton. And there's not a ton of free energy in here, because it's less, we're talking less than the order of the neutron minus proton. This means that the W is going to be very virtual, which makes it so this process is very slow, which is the reason why the fusion is still going on. If the W was much less massive, this fusion would happen very quickly, which would lead to the sun exploding and not burning for over 4 billion years, that it's currently burning for billions of years. Not 4 billion. Now, this is one of the many places where the mass of the W has a big impact, and where we don't need to measure it directly, but we can tell it has mass from this type of measurement directly. Now, because the Saramol is so interconnected, we can actually tell a lot about the W's mass just from these types of interactions and others. So, as I was talking about, the Saramol is very interconnected, and we can tell a lot about the W without measuring it directly and how much mass should it have. We can then compare measured mass and see, is their model correct? Is the mass of the W the mass we would expect based on all our other measurements? Well, when we're looking here, the blue circle uses information of the Higgs and other properties to predict what the mass should be based on the mass of the top quark. Now, as we can see, they don't quite overlap, where this is the measured mass of the W, and compared to what the predicted mass should be. But does this mean the Saramol is wrong? Well, not necessarily, because we can see the error bars are really big on the mass of W when you compare it to the difference of where we'd expect it to be. So, although this is an interesting fact of what we can see they're fairly different, it doesn't actually tell us if this is an implication the Saramol is wrong or not because of the large error bars. So we don't know if our watch is broken or not, or rather, it's the incorrect one. Now, the best way of actually telling more clearly, is this actually an implication the Saramol model is incomplete, is by lowering these error bars. If the mass doesn't move very much and the error bars get smaller, that would be an implication that the Saramol was wrong. Well, if the measured mass actually decreases and gets closer there, that would be good. That would remove that issue. So, how do we measure the mass of the W? Well, in order to measure the mass of the W, we have to create it. Now, if I want to create one W, the best way of doing that is to have quark fusion, where we can have a U and a D bar produce a W plus. The issue with this is that, well, in order to produce a W plus, we need to collide quarks, but we don't have quarks. We have protons that are made up of quarks. We can't just take two quarks at a set energy and collide them. So we end up colliding protons. And protons are made up of quarks. Now, you usually describe them as made up of 3 quarks, 2 ups, and a down, but that's not the whole picture, because those 3 quarks are held together by gluons, and these gluons, in turn, can split to become virtual quark-antiquark pairs. And this entire mess of stuff, each of which is carrying different momentums of the proton. And we also have issues where these types of interactions with gluon exchanges happening between them can also have overall effects on the quarks we're interested in producing the W. Meaning the entire system is very complicated. We're not just colliding 2 particles. We're colliding masses of particles that are all interacting at the moment of collision. So when a W is produced from a proton collision, what else is happening? Well, we've got the 2 quarks of interest that collide. We have to pick what quark and what antiquark are producing the W. We can predict what this type of interaction is going to happen. The Saramol does this type of prediction very well. However, there's also going to have other QCD interactions, strong force interactions, that are going to be affecting those quarks before impact that can affect the overall momentum and other parts of the W's characteristics. Now, these are shown in the diagram as soft QCD radiation interactions. They're going to be playing and affecting the final state W. Now, the next question is, why don't we just do the calculations for what these QCD interactions are going to do? Why can't we do those calculations? After all, we can calculate what this is going to do. Well, the issue comes with the quirk of the strong force. Now, the problem stems from alpha strong, which is shown here as a function of energy. Now, the issue is that alpha strong, the strong coupling constant, isn't constant, is dependent on Q, which is the momentum transfer of the interaction. Now, this comes to an issue with as Q decreases, alpha strong gets larger. Now, because alpha strong gets larger, and you can see here it keeps increasing, it'll eventually be greater than 1. Now, this breaks one of the great tools of quantum mechanics, in that we can't use perturbation theory. Now, perturbation theory requires that adding complexity or that the subsequent terms in doing the calculations have to be smaller than the terms before it. Once alpha is greater than 1, adding complexity actually makes the terms have larger and larger effects on the overall calculations, which means that in order to do a QCD calculation, we'd have to do calculations involving infinite gluons. That's not possible. So although QCD effects can be calculated when Q is large and alpha is small, as Q gets smaller, the calculations become at first impractical and then impossible to do. Now, as we'll talk about later, when we come to interpret our measurements, these effects are modeled rather than calculated. The data, like our measurements, are important to constrain these models. So, when talking about momentum of the particles, as I mentioned, each of the parts of a proton carries some of the momentum. The distribution of those momentums in quarks and gluons making up the proton is not calculated directly from QCD. As seen in both plots, where these are different Q squared levels, the majority of the momentum is carried by the real quarks, with the up and the down being the two that make up the proton. However, the probability of a virtual particle carrying an appreciable amount of the momentum is non-trivial in both of these, and you can see it gets higher as a higher Q squared. Now, PDFs, again, are not calculated and are estimated by various groups based on a variety of measurements, including some similar to ours. In particular, PDFs are important not only in W production, but also in earlier scatterers in the history of the particles that produce the W. As I mentioned before, there's a lot of stuff going on in the proton with a lot of other quarks, and those other interactions can affect the quarks that do produce the W. Due to the large number of variables that are involved in the production of W, high precise measurements are necessary to gain any useful information about the W. Now that we introduce the idea of the importance of the W mass and some complexities of producing it, let's introduce where we produce these and W so that we can understand why we start with a study of the Z. So the LHC is where this experiment was done. This exists on the border between France and Switzerland, and it's 27 miles in circumference. The data was taken from the CMS detector circled here. Now, the CMS detector, or compact muon solenoid, is a multi-purpose detector that exists at the LHC. Now, it is made with 4 different sub-detectors, with the centermost being the silicon tracker, outlined in black. This silicon tracker is what tracks charged particles. Because of the compact muon solenoid produces a strong magnetic field, those particles travel in a curved path, and by measuring the arc of the curve, we can calculate what the momentum is. Directly outside of there is ECAL. ECAL is a lead tungstate silane calorimeter, which measures the energy of electrons and photons, followed directly by HCAL, circled in red, which is the hadron calorimeter, measures the energy of hadrons. It is a sampling calorimeter made of brass and plastics, center layers in alternating layers, followed by the solenoid for which the detector gets its name. This solenoid can have up to 17 kiloamps going through it, creating a field of 3.8 Teslas. And last but not least, the muon chambers, which exist outside of the entire thing. The muon chambers are what measures muons. So, when talking about this, here's a cross-sectional view of how the particles interact with the detector. We have the photon and the electron here, and you can see both of them are stopped in equal and deposit energies. However, the photon with the dotted line here is not seen by the tracker, and the electron, it follows a curved path that is seen. Because of this, we can tell where the energy is being deposited, whether it's an electron or a photon that deposited energy in equal. Similarly, we've got a neutron and a charged pion depositing energy in HCal, which allows us to tell the difference between those two and energies. And last but not least is the muon. The muon is really hard to stop and measure its energy. Instead, we've got the muon chambers just measure their path. And again, because it's a strong magnetic field, we can measure the curvature of the path to calculate what the momentum is. So the CMS detector, we use a coordinate system described in XYZ, with Z goes along the beam line, Y goes straight up, and X goes towards the center of the LHC. We also include theta, which is an angle between a vector and the Z-axis, and phi, which is an angular measurement between a vector and the X-axis and the XY plane. Another variable that we use a lot is called pseudo-rapidity, or eta. This is shown here. Now, the reason we use pseudo-rapidity is at a hadron collider, particles tend to be produced at a relatively uniform rate over pseudo-rapidity, unlike phi unlike theta. Now, in 2012, we had collisions at a rate where, in 2012, which data was collected, bunches collided at a rate of 20 megahertz. That was once every 50 nanoseconds. Now, on the right, we show a plot of how often interactions happen in that. You'll notice that a lot of the interesting interactions happen at the kilohertz rate. That's much lower than the 20 megahertz. Because of that, we don't need to save data every event, and in fact, we don't want to, because we can't save all sorts of events that are happening at a rate of 20 megahertz. So instead, we need to figure out which events to save. What characteristics are there of an interesting event? In order to do that, we use a trigger system, a two-step trigger system. So we start out with the L1 trigger, which reduces the rate from the 20 megahertz to 100 kilohertz. Now, this has to run very, very fast. Because of that, it uses specialized hardware and a granulated version of the detector. If an event passes the L1 trigger, it's passed to the HLT, or the high-level trigger, which reduces the rate to about 400 hertz. Now, this can run at a much slower rate because it's being given information at a rate of 100 kilohertz instead of 20 megahertz. So it can use more generic hardware and regular computers in a farm and the complete event. If it passes the high-level trigger, it's safe to take. So, going back to W, how would we want to measure the mass at W? Well, I showed that there are two ways of producing the W, but this way it produces a U and a D bar. Now, this will end up producing jets of high energy. Now, the problem with that is that when you see here, these types of jets are produced through QCD interaction, quantum chromodynamics, just strong force interactions, and we don't really care about those. These happen at a much higher rate than the W. You can see it's over 2 orders of magnitude if we're talking about relatively low energy jets, 50 GeV. Because of that, it's very difficult to make a trigger that triggers on the W and gives us W information that isn't triggering a lot on jets and non-interesting events. Because of that, we tend to look at this process, where it produces an electron or positron, depending on the charge of the W, and a neutrino or antineutrino. Now, there's an issue with this, in that we can't see the neutrino. It travels right through our detector, doesn't interact. So we are unable to calculate the mass directly from this. But how can we figure out what the mass is? Well, if we can't do it directly, we do know that the properties of this electron or positron are going to be directly related to the mass of the W. If the W is heavier, we're going to be more likely to have a high energy one. However, at the LHC, the W is always produced and it's moving along the z-axis. The reason it's always moving along the z-axis is, if you remember the PDFs before, the partons that produce the W aren't ever going to have the exact same momentum, because the W is going to be going down the beamline one way or the other. However, because the beam's not moving much in the x direction, the W being produced won't be moving much transversely, it won't be moving much in the x or y direction. So the majority of the electron's momentum in the transverse direction will come from the W's mass. However, that W will have a bit of QT to it that we need to take into account. So in order to do these measurements, we have to make sure we're calculating that variable well. So once we have a simulation producing a W with a tiny bit of transverse momentum from simulations, we can compare that to what our real value is and see what simulated sample or theoretical values distribution match the actual data taken. And we can figure out the mass by comparing it to different mass simulations. Now, part of the issue here is we need to make sure that we're producing W with a time at QT. It doesn't have much, but when we're trying to get such a precise measurement, we have to predict that very well. The issue with that, though, is just as though we can't measure the mass of W directly, we can't measure the QT of it directly. And like I said, we need to make sure we're doing that very well. Well, rather than looking at the QT of the W, which we can't measure, we can look at a very similar reaction. So when QQ to Z to LL can produce two charged leptons, unlike the W, which is a very similar reaction of QQ to W to LL, which it produces a neutrino, and it allows us to measure the QT of the Z. And by measuring the QT of the Z, we can tell something about how well our simulation is predicting the W's. And this would help us, with this knowledge in hand, we'd be able to see if our simulation is doing it well, and then if it's not doing it well, that would tell us something about the uncertainty of the overall. So we can attempt to try to get their simulation to match better. Now, from here on, I'm going to focus on the transverse momentum of the Z rather than the W for the rest of this talk. Now, directly measuring the QT of the Z is, although we can measure it well, it's difficult to do it super precisely. The reason for that is we're subtracting two big numbers from each other. For example, if we had an electron, if we had on a one-dimensional plot an electron going in the x direction and a positron going in the negative x direction, we'd end up with a PZ of 3. And although these measurements are accurate within 10%, this one will have an uncertainty of over 100%. So although we can technically measure the QT of the Z, its accuracy is difficult. So how do we, what's a better solution? Well, we can use angles. Now, here we look at a variable called phi-star. Now, phi-star is a relatively complicated formula, but all it's really doing is looking at an opening angle between the two leptons. So as the Z is boosted more, that opening angle gets closed. Why do we do that? Well, when we're looking at the accuracy of these variables, and we look at a simulated sample of, we take what the simulation actually produced versus what the simulated detector saw, the QT is much less accurate than the overall phi-star variable, but the phi-star variable is highly correlated with the QT. So by measuring the phi-star, we can get an idea of whether the QT is correct with a higher degree of accuracy and smaller errors. The second variable that's interesting when talking about underlying events, which are dependent again on QCD interactions that we can't calculate, is rapidity, otherwise known as y. Now, here's what the rapidity formula is, but what's important is we can convert rapidity and calculate what the fractional momentum is being carried by the partons that produce it. This is going to be directly related to PDFs, which again are based on QCD interactions that we can't calculate. So these are the variables that we want to look at, but we need to decide what types of data we want to collect. So our detector, when we produce a Z, won't necessarily see it. If it produces if the Z decays and fires the electron straight down the beamline, we can't see it, which means that Z won't be reconstructed. So instead, we're going to look at a cross-section of all Z decays. We're looking at a cross-section calculated from Z's that decay within a very specific acceptance window. So part of our acceptance is require one of the charged leptons to have a PT of greater than 30 GeV, well, a rapidity of less than 2.1. And the second one we put slightly less stringent requirements on of 20 GeV of the transverse momentum and an A of less than 2.4. We also require the phi-star to be less than 3.277 and the invariant mass to be between 60 and 120. That's because, as you can see here, although a large amount of things can make an electron-anti-electron pair, not much is none really close to Z. So that's how we do our acceptance. But we also have to apply some electron quality cuts. The reason why we do electron quality cuts is just because we reconstructed an electron doesn't mean it actually was a real electron, or it could have came from something else. And although we applied our acceptance criteria so there won't be a large amount of fakes, we still do need to remove some of the fakes that do make it through. Now, here are two that we use for removing electrons that came from hadrons. Now, or hadrons that looked like electrons. Now, when we produce a mass of hadrons that go in some direction, every now and then one of them can decay to an electron. However, when it decays to an electron, a large amount of energy gets deposited around it because there's still a lot of hadrons going in that same general direction. Because of that, we can put isolation criteria and make it so that the electron doesn't have much around it. That removes a lot of the electrons that came from hadron decays. There also is, every now and then, this secondary cut, remember, is an H over E. That's the amount of energy in the hadron calorimeter over the amount of energy electron calorimeter in the same eta phi direction. The reason why this one works is because of the idea that if it's an electron, it should be stopped and deposit all its energy in ecal. If something's making it to hcal, it could be because it was a jet that made it through ecal that looked like, for a second before with hadron that decayed, but also could be because we have like a pi minus that looked like it might be an electron and still made it to hcal though. So we apply these cuts to remove electrons that probably didn't come from Z's. So let's start looking at the overall shape. Now, if we're looking at the QT of a Z, we can compare it to simulation. Now, this important point is that you can see here that when we're comparing to simulation, it's relatively flat, but it is bouncing up and down a lot here. Now, if it's flat, that's okay, even if it's consistently above. That's because we have a luminosity factor in there that could make the entire thing a little bit higher or a little bit lower. So we don't really care about that. We care about whether the shape is consistent and whether the shape is flat. Now we can see there's definitely something going on here, but it's a little hard to see anything clearly. When we look at phi-star, however, which is better at looking at the low region, we can see there's a very definite overall shape change of this. And this is also very consistent in both the electron and the muon channel. And last is the rapidity shown here, which you can see is decreasing the entire way, and there's obviously some disagreement here. Now, all these plots showed what we saw, but it didn't really give us the true Z distribution. Now, if we want to look at the true Z distribution, we need to correct for both background and detector effects. Now, background is relatively easy. We look at a simulate background sample and subtract it from data to find out what the distribution would look like. But that doesn't include detector effects. Now, in order to do detector effects, we unfold the data. Now, in the unfolding, we do a two-step process. Now, the first process deals with bin migration. Now, bin migration is when the real Z's phi-star falls into a different bin than it should. Now, to correct for these, we take a MAD graph sample, which is a type of simulation, and look at what the MAD graph was produced and what the simulated detector saw. And we use this to unfold the data using the de-Agostoni method. Now, we can see here that even in MAD graph, the majority of events fall in the correct bin. However, about 10% of events reconstructed fall in a different bin than they were generated. So using this method, we can unfold some of the data. This, however, doesn't do complete correction because this is only events that were successfully reconstructed and fell into a different bin. We also have to do an efficiency correction. This is a correction for events that just weren't reconstructed. So this is looking at the number of reconstructed events over the generated events that should have fallen in that bin. Now this part is done just using the ratios of simulations. On here I show two different simulations, and we can see that they fall within the error bars in the vast majority of events, except for the high tail where it gets a little sawtooth. But we just use one of these to do an efficiency correction. And we do this after we correct for bin migration. So how accurate is our values? Well, as I mentioned before, we really care about how well how flat the shape is, make sure it fits well. We don't really care if it's the overall cross-section's a little high in all bins or a little low in all bins. We don't care that much about that. So we do two different studies, one with the luminosity uncertainty, which includes that correction factor. And you can see here that this luminosity uncertainty is the vast majority of our total uncertainties. We can, however, cancel that out by looking at a normalized plots, both normalizing the data and normalizing the simulations, which lowers our uncertainties quite a bit. We're talking on the order of about 4%, I mean 0.4%, in the majority of bins except in the very high bins. These uncertainties come mostly from statistical uncertainties, the statistics of the data, as well as unfolding. Now the unfolding uncertainty comes directly from the statistics of our Monte Carlo sample that we use to do the unfolding. You can see that in almost all the bins, except for the really high phi-star bins, these are by far the majority of our uncertainties. Now it's an important point to note that when people were doing QT measurements of the Z, the uncertainties were on the order of 2%. That's quite a bit higher than we're getting of, again, about 0.4. So that's the data, but we also have to have a simulation to compare it to. How do we make these simulations? Well, we use a two-step process to make the predictions using a generator and a hadronizer. So first is a generator, which uses the Feynman diagrams to predict the quark interactions. But again, it just produces a quark, anti-quark, and everything in the circle region is done by it. In order to produce the hadronization, which is not predictable through perturbation, we use the hadronizer. It produces the rest of it, so it adds the rest of the quarks making up the proton, and also adds some QCD interactions down here that affect the quark that produce the W or the Z. Now, there's multiple different generators used, and they all have their pluses and minuses. Two of the popular ones used are MAD graph. Now, this one can include multiple final partons where it, as it's showing here, it's firing off two gluons. These gluons are high energy, so perturbation still works with them. There's also PALHEG, which can include loops here, but it produces one and only one high jet. Now this is then fed into the hadronizer. Now we use Pythia as our hadronizer. So for here I showed a simple example where we just had a quark antiquark produced by a generator, so no extra things produced by a generator, and fed into Pythia. Pythia will then add events in the order of hardness. So it will produce particles 1 and 2, where 2 will be the hardest jet it produces. And then it'll produce particles 3 and 4, with 4 being the second hardest. And then 5 and 6, with 6 being the next hardest. Now, an important point is that it doesn't just produce things in order of time backwards. This second particle can add QT to our initial one. So it can have final effects on, it can affect what happens with the Z. It can have those types of effects. So we can't ignore it. Now, another important point is that I talked about the fact that the PDF is dependent on the Q, the momentum transfer. Because of this, we don't use the same PDFs for the generator as the hadronizer. Now, a lot of studies have been done on the effect of the overall generator on these types of distributions. Not much have been done on the other effects that the Pythia could have on the overall measurement. So what are our final results of phi-star directly? Well, when looking at that, we look at the absolute case, we can see that MadGraph is probably the one that fits closest, and a number of bins it fits within the uncertainty, but it fits outside of them for a couple. Same with Pau plus Pythia 6 fits in a lot, but overall about a number of bins still fall outside of it, the majority I'd say, and Lesko has giant error bars, and hard to say much about that. Now, what happens when we normalize it? Because again, we can normalize it to see if the shapes are correct. That helps us understand if the standard model itself is. That lowers the uncertainties a lot, and we can see that in almost all these simulations, the majority of the bins fall outside of there. That's showing a problem with all the simulations. Now, a hint about what's causing this, or at least one of the things causing this, comes from these two. Now, you'll notice both these are Pau eggs, but one's plus Pythia 6 and one's Pythia 8. And you'll notice there's a very different shape in both of them. That's implying that the hadronizer is having a big effect on the overall shapes here, and the overall can be affecting the QT in a very noticeable way. Now, if we look at the rapidity distribution, I've shown here rapidity, and here I also did phi-star separated into the different rapidity bins. Now, you'll notice here almost all the simulations follow the same pattern except for MadGraph, which increases as we get to higher ranges. Similarly, we can see that the MadGraph distribution gets higher and higher as we get to higher rapidity ranges. Something to note is that all the general shapes stay the same of phi-star distributions in all rapidity ranges until the uncertainty gets large enough you can't tell much about the shape. So Pau egg plus Pythia 8 and Pau egg plus Pythia 6 do appear to cause some differences. What's the difference between Pau egg plus Pythia 6 and Pythia 8? Well, one thing I'd like to say is Pythia 8 is a completely different program written in C++, unlike Pythia 6, which is unfortunate. The reason I point this out is the fact I want to be very clear that it's not copy-pasted code. It is a completely different program. Now, some of the other differences is Pythia 6 uses a different hadronization PDF from Pythia 8 by default. And Pythia 8 uses a Gaussian with different widths to pick the px and py of the partons produced, while Pythia 6 uses a Gaussian with a constant width. Now, what is the width of Pythia 8? Or how is that calculation? Well, it's a relatively complicated formula we can see here, but I'd like to, this term, shown here, is a damping coefficient to make it so that high rapidity ranges, we don't end up with a ton of PT. So since our rapidity range is tends to be fairly low, this term is basically 1 for almost all our Z's produced. So looking at this term, what it says is that the width is approximately sigma hard if Q is much, much greater than Q half, and sigma B is basically sigma self if Q is very little compared to sigma half. So do the PDF and the new sigma B, are they what's causing the difference between Pythia 6 and Pythia 8? Well, in order to test this, I took Pythia 8 and tried to use settings to use the same settings as Pythia 6. Now, we can see that with red being Pythia 6, none of the changes we did had much effect in the high phi-star range. Now, in the middle phi-star range, if we switched Pythia 8, which is the dark blue, to and try to use Pythia 6's PDF, it actually improved and moved the theory closer to data and the majority of bins, but didn't make it closer to Pythia 6's distribution, which was a tad odd. However, if we changed the tunes, which means we changed the sigma hard and sigma soft to the exact same value, so sigma B stayed relatively constant throughout everything, we ended up taking the blue and turned it to the green, which was Pythia 6's tunes. This gave us a similar shape in the middle to low phi-star range. You'll see it dips more down here and actually gets the same sort of bump that Pythia 6 had, but doesn't match it completely. And then when we switch both the tunes and the PDF, we ended up with the pink, and it still did not match completely. So there's obviously something more inherently different between Pythia 6 and Pythia 8 than the tunes and the PDFs being used. So we can't explain that part of the difference. Now, can we use the tunes to explain the difference between the data and the theory? Well, when we change the tunes here, we can see that as we make the tunes smaller, we decrease the disagreement in low phi-star. However, that comes at a cost, because by decreasing the disagreement, more events happen at low phi-star. Those events had to have come from somewhere. In this case, they actually come from the middle phi-star. As we can see, the disagreement actually increases in middle phi-star. It appears that by changing these, any improvements we see here, we end up seeing a disimprovement here, and there aren't much effects in the high phi-star range. And does the hadronizer's tunes have much of an effect on the PDF? Well, not much. When I changed both the Pythia 8 to Pythia 6 tunes, or Pythia 8 to Pythia 6 PDFs for the hadronizer, we didn't see much difference. And that is very different than if I changed the generator's PDF. You see a fairly large, noticeable difference in the overall rapidity distribution. So the hadronizer doesn't seem to have much of an effect on rapidity, although it does seem to have a very large effect on phi-star distribution. So in conclusion, the phi-star measurement is fairly high precision measurement that allows us to accurately probe the consistency of the predictions of the data at a level not previously measured. It was found that there are significant effects from the hadronizer on the theoretical phi-star distribution, and therefore QT. These results were interesting and worthy of further study as the WMAS measurement efforts proceed. And reasonable modifications to PDF and sigma B hadronizer did not fully resolve the discrepancies. They may, however, be a step in the full solution or point to a new set of uncertainties that should be considered in the estimate of the precision of any WMAS measurement. Now, okay.
Well, thank you for the clear presentation. And do you have any questions from the audience?
Yeah, I do. I can't remember if it was phi or sigma, but what was the difference between the hard and the soft? Is that just...
So this one? So this is just what sigma b approaches if q is very large, and this is what it approaches when sigma is very soft.
So we just designated them hard and soft. just
Yeah,
for-
because it's the hardness of the interaction. Because q, the larger the q is, means it's a harder interaction. So really hard interactions approach sigma hard, and really soft interactions approach sigma soft.
Okay.
So the overall shape of the PT was mostly flat, while the phi-star had this weird motion to it.
Yes,
Is it that you're simulating the correlation wrong, or is it just you don't have the precision on measuring the PT?
but we don't have precision at measuring low phi PT qs. And an important point is those are the majority of the z's have low PT. If we looked at a plot of the PT, you can see that it definitely spikes in the low regions. So this is the region that looks like it has the most problem, is also the region with the most of them.
Other questions or comments? Okay, well, if not, well, then I'll ask the public to please step outside. Yes, and I guess electronic devices, including this one.
Oh, yeah.
That's a new rule.
No, I'll get that.
Good, yeah.